Hi, today I'm going to introduce how to solve problem J, sliding tiles. So in this problem, you're given an n by n grid, which contains tiles stacked at the bottom of some columns. And there are some vertical bars, which are placed at the bottom between each pair of adjacent columns. So there are n minus 1 columns. We define two operations. The first one is tilting right, which tilts all tiles slide to the right as far as possible. The second operation is tilt down, which makes all tiles slide downward as far as possible. So this is an example. So we have this grid, and there are some tiles as shown in orange, and there are some bars which extends upwards. And in this example, we first tilt right, which makes some tiles move right. Like for example, for this tile, it moves to the fifth column. And for this tile, because it was blocked by this tile, so it moves to the fourth column instead. So this is the tilt right operation. And then we tilt down, which makes all tiles move downward. So the task is pretty simple. You're given the tiles and some bars, and you have to determine the number of tiles in each column after performing both operations. So how to solve this problem? Well, first of all, we can make some easy observations. The first one is that tilting downward doesn't affect the count, which I think is pretty obvious. So we only care about tilting right operations. Because in this problem, the size of the board is pretty large, which is like 10 to the fifth power or something like that. We cannot simulate the movement of the block naively. So instead, what we can do is to do the sweep line method. So in this method, we simulate block movement column by column. And what we can do is, like for each row, we keep a counter of how many columns that row occupies. And whenever we encounter a tile for that row, we add 1 to that counter. And if we encounter a bar instead, we clear a counter because we know that these tiles would be blocked by this bar. So we clear the counters to set it to 0 and apply a range addition to the last columns we examined. So this is an example that illustrates this idea. Where in the first figure, we don't know which tiles it was be slide into. And so in the second figure, we add this column, which we see are 5 tiles. And then we encounter the bar. And because this bar blocks the movement of the first 3 rows, so we have to clear the counter for these 3 rows and set it to 0. And because the counter is 1, so we apply a range addition to the first column. And now we add a second column, which is another 5 tiles. So we add 1 to those 5 rows counter. And because there's no bar between the second column and the third column, so we don't perform range additions. And now we move on to the third column. For the third column, there are 2 tiles, so we perform range addition to those 2 rows. So the counter for these 2 rows are 2 to 1 to 2 respectively. And now we add uh, and now we encounter a bar, which is a length of 4. So so now we have to clear the counter for these 4 rows, and then we perform a range addition respectively. Like for example, uh, this row's counter is 2, so we add 1 to both 2, uh, column 2 and column 3. And we keep on doing this, and then we can simulate the right movement of the blocks. Yeah, so we can simulate the right movement of the blocks. So this is the pseudocode for the algorithm we just proposed. So C is the counter for each column, and R is the answer we want to output. So the pseudocode is displayed here, which describes the idea I just described. So it is pretty obvious that the solution represented is too slow, which is like O(n) squared time. So we have to speed up the solution. So the solution is pretty standard, is that we use one operation to perform the range addition part for the segments of same values. Like for example, if you have 5 threes in C, then it is equivalent to add 5 to the range of C of length 3. So what we can do is to use a segment tree to maintain the segments of the same values. And this is fast enough from a Mortise analysis because, as you can imagine, that each operation you do here and here will only add a constant number of segments. So like we will only need to deal with like an O(n) number of segments. So the time complexity of this algorithm is O(n) log n. Like and some extras I'll talk about here. So this problem in fact has many alternative solutions, um, either from testers or from other judges. So the solution one I'm going to introduce is to sort the number of tiles in some selected rectangles. So there's a fact that you can notice is that if the bar length of the grid is 0, then in fact that tilting right uh, will sort the number of tiles in each column. So this is known as the gravity sort. So of course you cannot split the board into too many rectangles, but there's a solution that you can split the grid into some number of rectangles, and then we just simply have to sort the number of tiles in some selected rectangles. So if you do this carefully, you can make the solution fast enough. So the second solution is to, based on the fact that recording the number of blank cells instead of the filled cells instead. And although many implementations of this problem is quite long, we have a surprisingly short solution that is around 70 bytes long from a tester. Yeah, which is pretty surprising, and it's also very clean. So thank you.